Okay, so welcome everybody to our first Graviticulus seminar of this second semester of 2021. Today the speaker is Gianni. Just as an introduction, he did his undergraduate and master's degree in the University of Cambridge in UK. He did his PhD in Queen Mary University of London, and also he did a postdoc in Universidad Nacional de La Plata in Argentina, and another postdoc in SEX in Valdivia in Chile. And now he's an associated professor of Universidad Adolfo Ibáñez. And today he's going to give us a talk about colliding vortices with internal structure. So Gianni, thank you very much for giving us this talk, and please go ahead.
Thank you very much, Francisca, and well, thank you in general for the opportunity of giving this this talk and exposing my research. So I'm very grateful for that. Today I will talk to you about well, some of the research I've been doing in the last couple of years, although it addresses or tries to address, let's say very broadly tries to address a problem which is much older than a couple of years. And I should start by showing you who I did this work with. This work, which is, well, this reference here, is in collaboration with Minoru Eto from Japan, Fidel Chapoznik Jr., because most of Latin America, and I say most of the world, knows Fidel Chapoznik Sr. He is the son, and Adam Peterson from California. So this is like a multi-continent collaboration between Japan, US, Latin America, and France. So you can imagine the Zoom meetings and scheduling Zoom meetings in terms of time zones. It was a nightmare, but it was done. And we were able to do this research. I should also mention that Fidel is now applying for postdocs. So I would keep an eye on that. It's an excellent candidate. Okay. So first of all, what is a vortex? A vortex is in general, it's a solitonic solution of some differential equation of some system. And they are important in various aspects of physics and I would say science in general. And the topic that most, well, that I am interested in the most is vortices in relation to quark confinement. So as I'm sure you know, we have still no idea or no real idea why quarks confine. We have no understanding of the detailed physics of quark confinement. Why this occurs exactly, no one knows, but there are various indications coming from lattice QCD or supersymmetrical results via the Seiberg-Witten scenario, and various other indications that some sort of solitonic solution resembling a vortex is responsible for the linear potential that we find when separating quarks, and therefore there should be some sort of string or some sort of vortex linking these quarks. And this is, well, hopefully responsible for confinement. And of course, the similar phenomenon happens in superconductors, which have nothing to do with quark confinement. In superconductors, materials which are superconducting, we know that magnetic charges confine thanks to the formation of vortices, or because of vortices in this case, which we know perfectly well that confine magnetic charges in these sort of materials. And the idea of confinement via vortices, at least the way Toft and Mandelstam proposed it in the 70s, is that the same sort of superconducting mechanism should be happening in QCD in the superconducting phase, where the analog of these superconducting vortices should form, and these should confine quarks. Of course, these vortices cannot be the same as the superconducting vortices, because the superconducting vortices, well, firstly, they confine magnetic charges, and quarks are electric charges, not magnetic. And secondly, quarks carry additional charges, which are color charges. And so the vortex that should form in between should somehow also have color flux, or should know about this color charges, which is where non-abelian vortices have emerged, which are, in a sense, vortices like the superconducting ones, but that have internal orientational moduli, which means that they have some sort of information in their inside which carries non-abelian flux. Okay, some additional ingredient inside these vortices, which corresponds to some internal manifold, which is something to do with color flux. Okay, so in this context, what we would like to do, and what I will present to you in this seminar, is how these non-abelian vortices can be constructed in their simplest form. There are many general forms of constructing, but the simplest possible. And what is their physics in terms of how they interact between each other? Okay, perfect. So what are non-abelian vortices? Let's start with the simplest model possible. Okay, non-abelian vortices you recognize here arise from what the usual Ginzburg-Landau model of vortices, which is just abelian-Higgs model. So you recognize here, I have the standard abelian-Higgs model. This is just abelian-Higgs. Or basically, abelian-Higgs happens from this model by setting chi equals to 0. If I put chi equals to 0 here, you'll see that this model reduces the standard Ginzburg-Landau abelian-Higgs model with a quartic potential. Okay, and you'll see that we have an additional ingredient here, which is chi, and this chi is a real field. It's real and it's a triplet, so it's a vector. It's just this index A goes between 1 to 3, and basically this means that chi lives inside the internal manifold, which is O3 in this case. It's just a vector which points inside the sphere. Okay, so chi is just a real vector. It points in one direction of this internal manifold, which is a sphere. Okay, and it couples in a very simple way to the usual Higgs field. And what we will show is that there are vortex solutions in this system which carry this extra ingredient inside, and this extra ingredient precisely brings about this sort of non-abelianicity or non-abelianity of the vortices which we want to describe. So we propose an ansatz, which is the usual ansatz for vortices. I don't know if you recognize, but in standard Abrikosov vortices, you have this sort of ansatz for the gauge field and the Higgs field. And now we have an extra ingredient, the chi field, which is just, as I said, this vortex, this triplet, this vector. And we choose some sort of component. This n is some sort of vector pointing in a particular direction of the sphere. I don't know, so let's say this North Pole, or one direction of the sphere, whichever it is. We solve the equations of motion for the system. Note that G equals 0 is a solution of the equations of motion. This is simply chi equals 0. Okay, so chi equals 0 is a solution which represents the usual Abrikosov vortices in this model. Okay, and we would like to find the solutions which are on top of this, where G is not equal to 0, so that chi can develop. Okay, so you solve this system numerically. There are no analytical solutions, no non-analytical solutions. Not even in the case for chi equals 0 are there any analytical solutions. And you solve this model, and you obtain some solutions. Let me just get rid of all this stuff. You obtain some analytical solution, some numerical solutions which describe precisely these kind of vortices which I was telling you about. So what you see here is this what I've plotted here on the left is this blue line, which sits on the origin, is the magnetic field carried by this vortex. So this is a radial plot. So you were looking at cylindrical symmetry. It's just looking at a radius around the center, which is at r equals 0. This is the Higgs field, which condenses in the vacuum and goes asymptotically towards its expectation value. And this is the G field, or chi, if you want, which condenses in the center of the vortex. Okay. So what does this physically represent? It represents some sort of vortex which carries inside it magnetic flux. You see that the magnetic field is peaked in the center of the vortex and decays outside. It's the Meissner effect. And it also carries a chi charge, a chi flux, which is this flux corresponding to this internal manifold, this O3 internal manifold. And this condensation of the chi field inside the vortex breaks the internal symmetry from O3 to O2 because we're picking a specific direction. So the only remaining symmetry that we have left is the symmetry around rotations around this direction that we picked, which is O2. It's the plane of rotations. Therefore, this is just a vortex, as I said, with some internal moduli. There's a vortex which has some internal orientational moduli on top of it. It's like an Abrikosov vortex plus some extra ingredients, which are these internal moduli. And what we can show numerically is that indeed the energy of the solution, or let's better say the tension of the solution of this vortex with the orientational moduli, is actually lower than without. So the system wants to develop the chi field rather than not, which was actually an unexpected result, but it means that actually this somehow lowers the energy of the system, which is nice, which is what we want. Perfect. So what happens inside the vortex in this case? Inside the vortex, we said we have some symmetry breaking, right? Outside, we know the symmetry breaking. It's the usual Higgs mechanism that we teach in, I don't know, graduate school, I guess, where you have, the Higgs field breaks the local symmetry in the vacuum, and therefore the gauge field acquires a mass. In this case, we have a real field, uncharged, inside, so it's global, inside the vortex, which breaks a global symmetry down to a subgroup from O3 to O2. And we know that global symmetry breaking makes Goldstone bosons, which in this case are not even by anything. So we have some sort of massless fields propagating inside the string. Okay, and these massless fields are described by just CP1. This is just a coset of O3 over O2, which is with this Lagrangian. So we have some sort of translational moduli. These are massless excitations which correspond to where I put the string, how the string can move on the radial plane anywhere, and this costs no energy. And we have no gapless excitations corresponding to these internal orientational moduli coming from this breaking of the global symmetry. They're just Goldstone bosons of breaking this global symmetry. Okay, so this kind of vortex has been used in many applications with many interesting physics behind this. Of course, it could be a whole seminar just giving applications of this kind of vortex. This is not what we're going to do today, but I'm going to mention them anyway. So, for example, one application that was studied is cholesteric applications of these kind of vortices. So these would be these kind of vortices where I make this internal orientation of this internal vector precess in a spiral along the string. Okay, and this has very nice applications in terms of liquid crystals, pneumatic liquid crystals, smectic liquid crystals, etc., etc. The theory of skyrmions, the theory of monopoles, where you can add internal moduli to this and make non-abelian monopoles, because they're already non-abelian, and skyrmions, where you can add these non-abelian moduli on top of skyrmions. Strangely enough, for skyrmions, it was the only occasion where we found that the energy of the skyrmions was lower without the additional field. which was a peculiarity. All other kind of subatomic solutions showed that chi field was wanted to develop, except the skyrmion. It's not exactly clear why still. And more exotic applications, like for example, ADS-CFT, which is, this is a completely different topic, but I will also just mention it, where you can solve these sort of superconducting vortices in a holographic superconducting setup. This is a lot more complicated than what we're going to do today, because it involves solving Einstein equations at the same time. So you have to solve the full Einstein matter equations in multiple dimensions. It's a different topic, but the end result is that you also find these kind of solutions in Einstein matter kind of setups, where some black hole, some ADS-Schwarzschild black hole creates some sort of Reisner-Nostrum patch on its horizon. The Reisner-Nostrum patch carries away towards the boundary the flux, the magnetic flux of the black hole, and this carrying away is done precisely via one of these superconducting flux tubes. And in this case, you can also make it non-abelian and describe all this kind of holographic physics, which is very nice, but as I said, a different topic. Perfect. So what kind of, where do these non-abelian solutions exist? Where does chi want to develop compared to where it doesn't want to develop? Because I told you before that the G=0 solutions were solutions of the previous setup. So it is not true that everywhere in parameter space, this solutions with this chi wants to develop inside the core of the vortex. There are some cases where it's preferable not to. And so numerically, you find this kind of phase diagram where you see basically on the left of this line are all the places in parameter space, parameters given by the mass of the gauge field and the mass of the chi field compared to the mass of the Higgs field, where chi wants to develop, so where the chi is non-zero in the center of the vortex, and regions in parameter space where it doesn't want to develop. Okay, and we are only interested in regions inside this dome where we can observe the condensation of this chi field, and then therefore we can also observe their interactions, how these things interact, and how these things move, and what their physics generally is. Perfect. So how do interactions between these vortices generally work? And this is a well, there is a detailed calculation behind this, which I am not, well, for simplicity, I'm not showing here. But basically, what one does is that one looks at the asymptotic region of these vortices, how the asymptotic region behaves. This is what Abrikosov did back when he won the Nobel Prize for it. You look at the asymptotic behavior of this of the far region of these vortices. You see how fields decay in this far region, and you compare which of the decays happens faster, and therefore which of the fields responsible for this decay is relevant or not in bringing vortices together. So if I have two vortices, I look at the interaction region, which is somewhere in between. If I assume that they're far enough, then the only thing I have to do is look at the asymptotic behavior of the fields somewhere in between, and I see which of the fields have decayed or not by that point, and therefore which ones are relevant in that region or not, and what forces they describe. Okay, so in the standard abelian case, without the chi field, well, one has this kind of behavior. This k here is a Bessel function, and it's governed, the decay of the Bessel function is exponential, and so the exponential decay is governed by these parameters, these mass parameters, m phi and m gamma. A here is just the distance between these two vortices on the plane. It's just a distance, how far I put them. So you see that if m phi is less than m gamma, then this term will decay before This term will be irrelevant in the intermediate distance. This term will be the dominant one, and therefore the force. Sorry, it's the opposite. I messed it up. When m phi is smaller than gamma, this term dominates because the exponential decay is slower. This exponential decay will be faster because m gamma is larger. It's like exponential to the minus m gamma, therefore it will be exponentially decay faster. Therefore, this term is the most relevant. And since this is a potential and this has a minus term, we see that the force is attractive. Okay, so what does this mean? If I sit at a point where m phi, I just choose the parameters. I choose a parameter where the mass of the Higgs field is less than the mass of the gauge field. Gamma here is the gauge field. Therefore, I expect two vortices to attract. Okay, and this is the what we call type 1 vortices. Type 1 vortices are vortices which attract in general in parameter space. And the opposite case, the case where m phi is greater than m gamma, therefore this term decays faster than this term. In that case, we expect, since this carries a positive sign, we expect the force to be repulsive. And therefore, if I put two vortices together, I expect these vortices to repel one another. Okay. And note that here I've added dot because this is only, of course, a leading approximation to the far field region, and one, of course, wants to include all perfect calculation. One wants to include also subleading terms, and subleading terms are actually very important, and they are extremely important for our discussion. But I will not show you this. I'll just show you the result of including these subleading terms in our discussion. Note also that type 2 vortices, the ones which have repulsion, are the ones for which we have formation of these famous Abrikosov lattices. So lattices of vortices. In this case, it is preferable for multi-vortices to not stack on top of each other, but rather to form regular arrays of vortices, which are observed in nature. In fact, I think I had a picture of this at the very beginning. These sort of arrays of vortices. So what you're looking at here is a plane on top of which we see a lot of vortices which are arranged in, well, it's not apparent in this case, but they arrange themselves in square or lattice or hexagonal structures. Let's say this kind of lattice structures, which do not happen in the case they're attractive. Of course, an attractive lattice would be a metastable or unstable solution, because if I move any kind of vortex, a little amount, it will stick to another. Okay, perfect. So this is the abelian case. What happens in the non-abelian case? So what happens when I add this extra chi field on top? Well, we add to this system this sort of potential. Okay. I know that the potential is, of course, chi is a scalar field, so I would expect this minus sign, so the same as the scalar field for phi. It's not a gauge field which comes with a positive sign, but it comes with this dot product of internal orientations. So you see that this minus sign at the beginning actually depends on how I prepare the two orientations of the vortices I want to make interact. If these vortices are orthogonal in internal space, if this chi field in one vortex points, let's say in the z direction or the 3 direction internal space, and the other one in the 2 direction, then this term vanishes at leading order, in fact, has no relevance. If I prepare them in an anti-parallel configuration, then this dot product will be negative, and this will be a positive interaction. Okay, so a repulsion. And if I prepare them parallel so that this is positive, then I expect them to be attractive. Okay, and the whole, this whole study and this whole seminar, if you want, is precisely studying if this is correct, what kind of interactions we expect for these vortices, how they interact, and to go and actually check via scatterings and via collisions if these things are true. So in general, this is just the table of all possible cases given by what orientations I consider and how the mass parameters are related to each other. Okay, so in the case that the lightest mass is the gamma mass, so we're type 2, then for parallels I expect repulsion, for orthogonals I expect some repulsion, because in that case it's just dominated by the abelian case, and the antiparallels I expect some repulsion, etc., etc., etc. So I just make, this is basically just a table of which one's the lightest between m chi, m phi, and m gamma. That one will dominate the far field expansion. And what are the orientations of the two vortices I consider interacting? Okay, and this is for the case of vortex-vortex interactions, and this is the case of vortex-anti-vortex interaction. The only thing that changes between vortex and anti-vortex is basically one has a winding in one direction of the Higgs field, the other one has a winding in the opposite direction. The fluxes are opposite, and so when they meet, they just manipulate rather than collide and scatter. Okay, so the rest of this seminar will be talking about, I'm trying to confirm this kind of analytical approximation and having some fun basically on collisions of solitonic solutions. Okay, so how do I make these things collide? Let's prepare my system. Okay, so I have remember that I have a static vortex solution, right? I have a solution of those original equations of motions which I prepared in a radial plane. And now I want to prepare two of them separated by some distance, and I want to send them towards each other. And I want to look at how they interact. Precisely because I expect some interaction analytically, I want to confirm it, and mostly I want to find new physics. And hopefully this new physics, especially the interaction between these orientational internal moduli, I can hopefully, or at least that is the big hope, be able to relate to QCD and confinement and what happens between the vortices that are close to each other, for example, in baryons, right? If a baryon carries a vortex between each quark, then hopefully I know how these things interact between each other, etc., etc. I will not be able to go as far as even speculate on what QCD does from this model, but it's at least the first indication. Okay, so I have these static solutions. So now I have to make two of them, and I have to collide them in a plane. So firstly, I have to change my radial solution to Cartesian coordinates, which is why we see now x and y's rather than r's. And I have to separate them by a distance a in the x direction. Right, so I make two copies of them. I separate them by a in the x direction. I separate them by b in the y direction. So I now put an offset. This is called the impact parameter of scatterings, as I'm sure all of you know. And then I have to send them towards each other with some internal velocity or some initial velocity u. And of course, it has to be relativistic. I can't just assume that I'm sending them a small velocity, because I'm interested in the whole velocities of scatterings up to 0.99 c or whatever. Okay, so this is the way you do it. You just take your solution, you prepare it this way, you separate them, you boost them in the x direction, you give it some initial velocity, and of course, I have internal fields here. I have internal orientations. This is a sphere. We have an O3 sphere, remember? So I have to be able to send them at whatever internal orientation I decide. So I rotate the internal vector in this O3 by some angle alpha, which I decide. And then I look at scatterings with different alphas, different velocities, etc., etc., etc. And I have to do this for all the gauge fields, for the internal fields, for all the angles possible. Okay. Of course, if you have a question, please feel free to ask me at any point. So this is the general picture of what I will do. I'm preparing two vortices separated by A in this direction, which is I will call the X direction, by B in this direction, which I will call the Y direction. Most of what I will show you will be at B equals 0. I have some results with input parameter if you want, but it's not particularly new or particularly relevant to this discussion. And each of these vortices will carry an internal sphere with some angle of this vector on it, and I will make these things collide in real space, so solitonic space, and internal space. These two spheres will meet, will interact, and these orientations will do something, which I will show you soon. Okay, so these things are my initial states, and I have to evolve them via the equations of motion of the system. Of course, now these are time-dependent equations of motion in Cartesian coordinates, no longer in radial space, for all the components of the gauge field that are relevant. I know I no longer have an A theta, I have an AX, I have an AY. I can no longer use the radial ansatz for the gauge for the Higgs field. I have to solve for the real and the imaginary parts, and then construct what the modulus is and what the phase is. I have three equations for chi, one for each component of this internal sphere, etc., etc. So I just have to evolve these initial conditions numerically to see how these things collide. So at the beginning, I wrote a code for this. All of this is coded in Mathematica. I wrote a code for this. I will show you what this code is. I wrote a code for doing this. So this is solving in 2+1 dimensions, these solitons, and making them collide. Okay, this was my initial code, which I prepared to solve on CPUs of my system. As you can see, it is particularly involved in a sense that it is not particularly hard to code. It just involves a lot of CPU manipulations, which is very time consuming, extremely time consuming. So let's say we had some sort of eureka moment after we realized that this kind of calculations were taking something like a day, around 1 day, to observe one collision, okay, done on CPUs. But we realized that Mathematica has a neural network implementation, which has nothing to do with solving partial differential equations, absolutely nothing to do. And it's usually used for machine learning, this neural network applications. But we realized that we could rewrite our evolution equations in neural network language so that Wolfram understood this evolution as a machine learning evolution rather than just a standard Runge-Kutta evolution, okay? And this allows to use GPUs, which are these sort of things that you have in your computers, rather than your processors. And this rewriting, which you can see here, is done in sort of, so what you see here, this, for example, is a neural network of one of those equations. So you see here, an input comes in, it goes through some manipulations, which are additions, multiplications, divisions, etc., blah, blah, blah. It is recombined in neural network language and it's a graph of neural network language, which is interpreted by machine learning in this way. And an output is given, which is the process of this neural network happening, okay? But as I say, the beauty of this is that we can pass this through GPUs rather than CPUs, and this was around 125 times improvement. So I can't do the maths in my head, but 24 hours divided by 125, I don't know, it was something like a day to 10 minutes or less, okay? So this basically opened the possibility of doing basically anything you want in this system, rather than having to wait for a long time, which is also what it was done in the literature before. In the literature before, of course, no one knew about GPUs and they were never used. And so this not only made us do things faster, it also allowed us to go to places in soliton scattering where no one went before, which is fun, basically, because we were just like, okay, well, let's see how far we can push this now that we have this amazing technology. And well, I will show you at the very end some stuff which, let's say, was, I don't know how relevant it is to physical models, but it was definitely fun, at least for us. Okay, so I also, if you guys have PDEs to solve and that they require a long time, I recommend looking into this sort of neural network language. It is a massive improvement, especially if you have good GPUs. Okay, so what are the simulations we found? Okay, so let me show you this one. This is the first one I'll show you of many. Okay, so this is what they generally look like. Okay, so here I'm scattering two type 1 vortices, vortex to vortex, in the parallel channel. So what we're looking at here is the chi2. So I prepared two vortices which point in the two direction of internal space. They're parallel in internal directions. And I expect this to be an attractive channel given the table I showed you before. Okay, and I send them at around half the speed of light. I send them towards each other, they find each other, they scatter at right angles, which is usually the case, but since it's attractive, they kind of want to come back. And if I let the system evolve enough, they're attractive, so there's an attractive interaction, and they slowly go towards each other and start bouncing in this direction towards each other. If I send them at higher speeds, then they will find each other, they will scatter at right angles, and they will keep going at right angles for further and further and further until eventually something kicks in and the attractive force is enough to bring them back in. Okay? Let's do the same thing for the repulsive channel. Now I am at the type 2. Now I expect these parallel vortices to be repulsive. Now I am in the case, just to show you back, I am in this case. Sorry, no, parallel repulsion here. I am in the type 2, while before I was in the type 1. Before I had them attractive, now I have them repulsion, but still parallel. Okay, so in this case, I expect them to repel. So I bring them towards each other, but they repel. They don't like each other. So they're like, well, you know what? I don't want to scatter with you because you repel me. Okay, so they repel and they go back. But if I scatter them high enough velocity, if I am some sort of, I don't know, if I force them to interact and to be together, then they do indeed scatter. They scatter at right angles. The right angle scattering is actually something that is common and previously known about vortices interacting. Okay, but now of course they are repulsive. So once they scatter, they will always be asymptotically. They will never find each other again because they're repulsing away from each other, and they repel. Note that also these waves that you're seeing here in this collision, the waves are waves of internal space. We're having some sort of, this is propagating in the sphere in terms of how this orientation is sitting on the sphere. Okay, but once they repel for at least this channel, they find each other, they're parallel, they find each other, they scatter, and they still are parallel, right? The vortices themselves, they're parallel going in, they have the same orientation, they're parallel going out. They have the same orientation. Parallelativity or orientation seems to be preserved in the scattering. Okay. Okay, so now let's do the anti-parallel case. I prepare one up, one down, I send them towards each other. I expect this to be repulsive. Okay, so I send them towards each other. If I don't have enough velocity, they don't find each other, but they repel. They don't really like each other. So we are confirming the analytical solution. If I send them at a little higher speed, so not 0.9, 0.8, then I find a new interesting phenomenon that was never observed before. And it's the following. They see each other, they find each other, and somehow they interchange their orientations, but they don't scatter. We know that they don't scatter because if I plot the phi field rather than the orientations, these simply meet and repel. This is the same scattering as this one. Only this is for the Higgs field, this is for the internal orientations. Somehow, when they meet, something happens for which they seem to interchange their orientation and yet not scatter. It is still a mystery to us, so we have no idea why. They simply don't want to maintain their orientations they had and just repel. somehow the orientation seems to delocalize in the region in between and interchange between each other. They don't pass through each other. That doesn't happen. They interact and they tell each other that you should, okay, you take mine, I take yours, and we'll never see each other again. There's some sort of interaction pre-scattering that interchanges orientations, and this was completely unknown, and there is still no idea or complete idea as to why this happened. Finally, if we send them with enough velocity, like a lot of velocity, towards each other, then not only do they meet, they interact, now they scatter at right angles, but they scatter in parallel orientations. Right? They meet, firstly, note the Lorentz contraction, right? Where I'm at 0.9 C. So you can actually see the Lorentz contraction of these vortices going in. And they interact, something happens, we don't know what it is. And they interact, they scatter because they come out at right angles, but they come out parallel. So I prepared them like this, something happens in between, let's scatter, one of them turns around, and then they scatter at right angles again. Okay, so this sort of mechanism is what the paper is all about, why this happens, what happens exactly, what interpretations we could give to these things, etc., etc. And the long story short is that basically we have no idea why these things happen. The system is completely highly nonlinear. We have no idea why this sort of behavior is seen. So what we basically did is just report on our findings, okay? So this is another case where they're anti-parallel, but in this case, repulsive. So this is we expect similar stuff, right? Anti-parallel repulsive, anti-parallel repulsive. We expect this to be kind of similar. We see that if we approach each other with small enough velocity, nothing really happens. Once we crank up the velocity a little bit, then we observe the similar phenomenon that we said before. They interchange their orientations, but somehow do not scatter. While if I go high enough, then these things scatter, take a long time, but eventually come out and scatter as parallel orientations. This case is more interesting because it also allowed us the possibility to observe or to try to observe these sort of metastable states where nothing happens. It seems like nothing is happening for a long time, right? In this particular case, it seems like they scatter, nothing happens for a long time, and then somehow they both nucleate again as parallel orientations. And understanding why this happens and when exactly this happens and how this is related to the parameters was something that we also investigated or tried to investigate. Very good. Are there any questions so far? No questions. Okay, so now let's look at more cases. So in this case, they are, this is scatterings of vortices and anti-vortices. So I'm sending a vortex and an anti-vortex towards each other. So what I expect is some sort of annihilation. Okay, and in fact, this is what we see. I send one vortex towards each other.
Gianni, you have 5 more minutes.
5 more minutes, okay. I send one vortex towards each other, they annihilate. And well, this is observed pretty much everywhere in all these VB bars annihilation. Since I have 5 minutes, I won't show you more of this. We find some sort of nice phase diagram where we confirm this table that I showed you before of what vortex is which one. We divided this internal space where the kind condenses into type 1s and type 2s inside there, which ones condense and which ones do not. And then, well, these are orthogonal orientations. I will skip them because I don't have enough time, apparently. There are some non-zero impact parameters ones. So ones where we separate them also in the y direction. So we introduce some angle and you see that they scatter at some some angles, etc., etc. But in this last 5 minutes, let me show you the fun we have with pushing our system. So we started looking at multi-vortex interactions. And these were not seen before, or at least never tried before. So sending multi-vortices towards each other. And you see that they do really funky stuff. They try to, let me show you the high velocity case. They have some sort of metastable states which renucleate. Then they have one big vortex state. Then they sort of like more metastable states, they separate. We had a lot of fun with this stuff. Now, maybe I will go into more speculative cases of high velocity. This is 4 vortex interactions. We send them towards each other at extremely high velocities. You see that it's a complete mess. We don't exactly understand what is happening there. But you also note that we send them at right angles and they come out at right angles, but rotated by 45 degrees, right? They go in here, they come out here in this diagonal, which is also something that, well, it's the same phenomenon as what you see in the case of 90-degree scattering, but in this case, at least it's for multi-vortex scatterings. And of course, we had a lot of fun by pushing this system towards more incredible cases, like, for example, 6 vortex scatterings, where we pushed, this case, we have 6 parallel vortices, which come in a hexagonal symmetry, and somehow they go out with some non-hexagonal symmetry. Why this happens, we have no idea. Why the symmetry would be broken is completely unknown to us. There is no literature on this topic anywhere. You see, these are crazy scatterings. This is what happens in Higgs space of the same scattering. Somehow the symmetry seems to be restored inside. It's extremely messy. But here you see the final states that come out. These final states correspond to the same final states you see here. And finally, in this last minute, we push this forward even more to look at 3D scatterings. So now it's solving the full equations with 3D flux tubes. So not only am I putting vortices on the plane and scattering them, I'm actually using the full flux tube. I'm pushing flux tubes towards each other. And what this gives me now is the possibility of changing the spatial orientation of these vortices, right? I can scatter a flux tube going in this direction with a flux tube going in this direction. And we explored the scatterings of these kind of systems, what these vortices want to do. This is a normal scattering on right angles. This is the kind of stuff we observed before. But now we can look at stuff, for example, like this, which was never observed before. These kind of scatterings, what happens? You see that this is, for example, relevant to cosmic strings. When 2 cosmic strings supposedly meet, what happens is they interact, they separate, they go in each other's ways. What happens now when they interact, for example, at right angles or anti-parallel? Well, you see that, for example, they do similar stuff, but let me show you one of these. Right, what happens when they're repulsive? They meet and they form some sort of kink structure inside each other. So in this case, the orientation is up, in this case, the orientation is down. There's some sort of kink developing because of this collision of these flux tubes. And then, of course, even more exotic cases of, for example, what happens if we put multi-vortices in? What can we do with these interesting cases? And we see, for example, in this case, it's repulsive, as is clearly seen. The vortices don't want to meet, don't want to do anything. What happens in the most exotic cases of them all, when they attract and we send them towards each other? Then we can form these sort of intermediate states, this intermediate flux tube ring state, which is reminiscent of what is known as a vorton, which are metastable states of like vortices which have some circulation, and these vortices are metastable. And in fact, we see they decay and how they decay and what time they decay. All of this is possible thanks to these numerical simulations, which you're seeing here. I'll show you this one again briefly. And therefore, in conclusion, these vortices show an extremely rich structure inside. They have a massive parameter space of collisions that we can do with them, how they behave, what they do with each other, etc., etc. What we have to do now is to continue exploring the three-dimensional case, what kind of structures we can form between these vortices, especially if they're reminiscent of these quarks and baryons or flux tube. How can we arrange them in sort of like baryons shapes, and how these things interact between each other. Of course, holography would be an extremely interesting place to look at next. However, this is extremely hard because it would be involving collisions of vortices on black hole horizons, solving relativistic Einstein matter evolution equations. So it's an extremely hard thing to do. The equations are disgusting, like they're extremely hard equations, even to just write, and to solve them it's even harder. But this is where we're looking at now. We're looking at solving holographic systems of things which move on black hole horizons and try to find each other and meet. Okay, thank you. Thank you very much.
Thank you so much, Gianni, for your very nice talk. Francisca got disconnected because she's mentioned before that she's at the beach, so the connection is not very well. So I'm going to continue with 10 minutes of questions. If anyone has any question for Gianni, please tell me.
I don't know if anyone is here, so except you.
No, there's supposed to be like nine persons.
I am here, sorry.
How are you, Marcelo? How are you doing?
Hi. Thank you, Gianni, for the talk. I arrived a little bit later, but anyway, I enjoyed it a lot. What is the possible scenario in the context of QCD? You mentioned something, but perhaps I didn't got it.
So QCD, I mean, ideally, what we would like to do. So here we have a system where, okay, let's say a baryon, right?
Yes.
This is a baryon, supposedly. Right? Actually, I think the lattice calculations show that the actual baryon is more of a Y shape for some reason. This is still not really known, but apparently a baryon is more like this than like this.
Yes.
But so now we have a system where we can actually do real four-dimensional simulations, so in a box plus time, of how this, the non-abelian version of this, so the one that carries color electric flux, actually interacts with this. So the idea is, okay, let's say I construct this by hand. Is it stable? Is it not stable? What will it evolve to? Is this one stable? And what about this one? Is this one the stable one? Now I can actually simulate it. That's the whole point. So in QCD, of course, this is a lot harder. In QCD, you have fermions, right? And we don't know what mechanism, unless Seiberg-Witten is true, we don't know exactly what condenses and if this is the same kind of vortex. But
okay,
assuming that it is, we can simulate it.
Thank you. And a very short extra question, please. When you talk about this lattice of vortices, because of vortices, I mean, there is something like if phase space, I mean, not a phase space, a phase structure, I mean, phase transitions inside this lattice, depending on the parameters, I mean, some strength interaction parameter, and how can you get it? Because it is much harder than the Ising model, certainly.
But you're talking in terms of the Abrikosov model or the model with internal orientations?
No, the Abrikosov model.
Okay, the Abrikosov model.
Perhaps you know it, but I don't know very much about it.
So you're talking about this kind of solution, right? Yeah, the Abrikosov model. Yeah, I mean,
Yeah, exactly. This one.
yes.
Yeah.
So what you have to change in the pure Abrikosov model is this parameter kappa, which is the relation between the mass of the phi field and the mass of the A field. The
Yeah.
critical point, or the BPS point, is this kappa equals 1 over square root 2. At this point, you have no interaction whatsoever. It's BPS, right?
I see.
But
Okay.
if the ratio of the mass of the Higgs field, so it's the mass of the Higgs field divided mass of the A field, that's kappa. If the mass of the Higgs field is smaller, then you have type 1s. You do not have a lattice. Lattice doesn't exist in type 1 because all vortices will coalesce into one of a large flux.
Wonderful. Okay.
And type 2, you have lattices.
Thanks a lot. Yeah.
Great. Any other question? I'm sorry, Marcelo, you wanting to say something
No.
more?
I wanted just to thank again.
Okay, sorry.
Thank you.
Okay, Gianni, I also have actually a question. So you were
Okay.
mentioning that the simulation you were doing with GPUs and like a machine learning algorithm,
Yes.
and you could improve your by 125.
Mhm.
So I was going to ask you which algorithm are you using and how you validate the result.
Okay, so this is a standard Runge-Kutta, fourth order Runge-Kutta evolution. This is the standard algorithm I'm using. And how I validate the result. I mean, okay, without the chi field, standard two-dimensional vortex scatterings were already done, and these we can reproduce with this mechanism. How to validate the ones above that? Well, there is no validation because they're new in this sense. But all the results, if you're asking about numerical precision, all the results are checked at machine precision. So they're extremely accurate results. In fact, one of the amazing things about these GPUs is that you can even push your code to like lattice spacings, which are extremely small because it's so fast. It's just so insanely fast. It's really good. I recommend you, if anyone has stuff to do in PDE solving, if you can translate it to neural network language, which is not easy, by the way. It's not easy. That's a lot of coding to put these things. It's worth it.
Yeah, that's great. That's great. Thank you.
Sure.
Okay, so if there's not any more questions, let's please thank. I can thank myself to Gianni.
Thank you.
And then, okay, we can continue with this seminar next week. So thank you all.
Perfect. Thank you. Goodbye.
Goodbye.